Welcome to this lecture. This is a short lecture. I thought some of you might not be comfortable with some results of Bessel functions which we have used, and then I found also that you might have studied Bessel functions, but definitely not some of those properties. So I thought it would be useful to have a short video on that. I will try to explain some of the concepts of Bessel function which we have used in the proof of bunching process in Klystron. First of all, let me define again once more the Bessel function of first order, rather first kind, which is denoted as J alpha of x. So there are several equivalent definitions, and one of the definitions is based on the series. So that I will write like this. So here is the definition. It runs from minus j to infinity, and then this is minus 1 to the power j divided by j factorial. Then this is a gamma function. Okay, gamma function, and then x by 2 to the power 2j plus alpha. And you can also, so now if alpha is integer, then we write suppose jn of x, which has an alternative definition which you have seen. This is mostly used 0 to pi cos of n tau minus x sine tau d tau. Now we need to prove one important identity which has been used. So that is, if you replace this j of n by minus n of x, then that is equal to minus 1 to the power n jn of x. So this is the identity actually which has been used in the proof of finding the Fourier series of the current in cavity, this catcher cavity is written. To prove this, we use the series definition of Bessel function. So I will first define j minus of alpha times x. So I will be using this particular definition of Bessel function. See, these two are equivalent. Okay, for alpha integer, these two are equivalent. And what I get, I can just replace alpha with minus alpha, and I will get this equation. Simple. I have just replaced alpha with minus alpha. I can rearrange some terms and write like this. So first of all, x to the power minus alpha, then this 2 to the power 2j minus alpha, I will write here separately, then x to the power 2j. Nothing difficult, so I have just rearranged the terms here. Now let's first explore the behavior of gamma function at different points. Now look at this. So this is gamma of j plus 1 minus alpha, right? Now we are going to consider a case where this alpha tends to n. It becomes an integer, and this j can take value from 0, 1, 2, so on and so forth, right? So you see for different values, suppose if you take alpha tends to n, then first of all for j is equal to minus 1. Okay, so now we start from 0. Wait, so j is equal to 0, j is equal to 0, so it becomes gamma of 1 minus n. Okay, so now for n is equal to 1, it becomes gamma of 0. Similarly, if you take j is equal to 1, then it becomes gamma of 1 plus 1 minus n. Okay, so it becomes gamma of 2 minus n. Now depending upon the size of n, so if you take any n which is greater than 2, this will be negative. Suppose if you take n is equal to 3, this will be gamma of minus 1, right? So if you consider from j is equal to 0 to n minus 1, now you take the n minus 1 term, so gamma of n minus 1 plus 1 minus n, so this is gamma of 0. Similarly, if you take n minus 2 term, so gamma of n minus 2 plus 1 minus n, it becomes gamma of minus 1. If you come back from n minus 1, then if you take n minus 3, so it becomes gamma of n minus 3 plus 1 minus n becomes gamma of minus 2. So we need to understand the behavior of gamma function at negative integers. At positive integers there is no doubt. Suppose you take j is equal to n or n plus 1, so on and so forth. So at j is equal to n, it becomes gamma of n plus 1 minus n, which is gamma of 1, which is 1 factorial. Then if we take n plus 1, so n plus 1 plus 1 minus n, it becomes gamma of 2, which is 2 factorial. So for these values of j's, our gamma function is well defined, but we need to understand the behavior. You may now say that gamma of 0 is 1. That is defined to be 1. Actually, it is 1 on one side of the limit. It is not 1 on both sides of the limit. Okay. So let me illustrate this concept in Octave with the plotting help. I will not prove it right now, but I will illustrate it. Here I will first define x as x equal to, suppose I take minus 1.1, then gap of 0.001 up to, suppose I will take 0.1. okay, this is what I take as x, and I will plot x and gamma function of x. So here is what you get. Now let me zoom it. If you see, this is the scenario at x. First of all, let me zoom it here. You can see the discontinuity. Okay, actually there is a discontinuity. So you can say that in fact, if you see to the right of 0, it tends to infinity, and to the left of 0, it tends to minus infinity, right? You can clearly see this. And same is the case at minus 1. At minus 1 also there is a discontinuity. In fact, in limiting case, it tends to infinity. If you take minus 1, left side of the minus 1, it tends to minus infinity. Okay, now let me plot it for some other negative points. Suppose I redefine this x to be, let me take it here as 2.1 and here as 0.99, okay, or 0.9, and then plot it. See again the same behavior. There it also tends to infinity as it goes to the right side of minus 2. See here, minus infinity. There's discontinuity, and similarly at minus 1. So this is the behavior of gamma function at every negative integer. So what does it mean? It means if you take a gamma function, gamma of, suppose I will write here x. So x is used for some other purpose. Let me write some other thing. Suppose gamma of y. Okay, take its magnitude and limit y tends to some negative integer, suppose minus of suppose k. Okay, where k can be even 0, 1, 2, 3. So it is, suppose it is limit y tends to minus 1, limit y tends to minus 2, or even limit y tends to 0. So in all these cases this tends to infinity. Okay, this gamma function tends to infinity. So it means that now you check this gamma of 1 plus alpha minus J, I think it is j here, yeah, j plus alpha minus 1, right? No, it is j plus 1 minus alpha, I think this one, yeah. Now you see, as alpha tends to, so as alpha tends to n and j is equal to either 0, 1 up to n minus 1, the internal term, this becomes either 0 or minus 1 or minus 2. It tends to either 0. So j plus 1 minus alpha tends to either 0 or minus 1, minus 2, so on and so forth, depending upon the value of j. So for all these values of j, this gamma of j plus 1 minus alpha, it tends to infinity as limit alpha tends to n, and for j equal to 0, 1 up to n minus 1. Okay, it tends to infinity. And for all other values, suppose for all other values means j plus 1, I will now let alpha equal to n directly here, and for j is equal to n, n plus 1, so on and so forth, it will become the famous formula, it will become j minus n factorial, right? You know that gamma of 3 is 2 factorial, gamma of 4 is 3 factorial, so gamma of n plus 1 is n factorial. So it is here gamma of j minus n plus 1. Okay, so that is why it is j minus n factorial. So hence we can then write, so when for j is equal to 0 to n minus 1, when gamma function tends to infinity, look at this. So when this term tends to infinity, so it means the coefficient of x to the power 2j, this is 1 by gamma function, this will tend to 0, right? So 1 over gamma of 1 j plus 1 minus alpha, this tends to 0 for j is equal to 0 to n minus 1 and alpha tending to n. So we can then write the gamma function as jn of x equal to, in fact is minus n, okay, minus n of x equal to, so I will now start summation from j is equal to n to infinity. Why? Because from j is equal to 0 to n minus 1 the terms are 0, then rest is same, minus 1 to the power j x to the power 2j minus n divided by j factorial 2 to the power 2j minus n times j minus n factorial. Now I will do one thing, I will let j minus n be equal to some k. So as j equals n, k equals 0, infinity remains here same, minus 1 to the power j, so hence j is equal to k plus n, so I will write here k plus n, x to the power 2 into k plus n minus n divided by j factorial means k plus n factorial, then there is j minus n factorial, that is k factorial, then there is 2 to the power 2 into k plus n minus n, right? So this can be written as summation k equal to 0 to infinity, then I will write here minus 1 to the power k and minus 1 to the power n x to the power 2k plus n divided by, now see this k plus n factorial and k factorial, I will write k factorial as it is, k plus n factorial I can write as gamma of k plus 1 plus n, right? And then 2 to the power this is 2k plus n. This can be exactly written as minus 1 to the power n here, summation k is equal to 0 to infinity, then minus 1 to the power k divided by k factorial gamma of k plus 1 minus n, then x by 2 2k plus n. Now if you look at this, this is exactly j n of x, right? Except that instead of I is equal to 0 to infinity, j is equal to 0 to infinity, we have k is equal to 0 to infinity, and the extra term here is minus 1 to the power n, jn of x, and remember we were computing j of minus 1 of x. So hence we have proved this identity. The only thing we used was gamma function's behavior at negative points. That proof of that is little bit again lengthy, we will not go into that. I have demonstrated that using simple numerical summation. Now I can write this in another way. So what I can say is, suppose if n is even, so some n is equal to some 2m, so then I can write j of minus 2m of x is, you know, minus 1 to the power 2m will be always 1. It is even number, so it is j of 2m of x. So this is for even m, and for odd n is equal to suppose 2m plus 1, I will get j of minus 2m plus 1 of x. You know, for odd minus 1 to the power n will be minus 1, so it is minus of j of minus 2m plus 1x. So in other words, j of minus 2 of x is j of 2x, j of minus 4 of x is j 4x, so on and so forth. and j of minus 3 of x is minus times j3 of x, and similar for other terms. Now coming back to yesterday's argument. Before recalling the yesterday's lecture, I will try to convert the notation so that it is consistent. So we basically had j minus n of, I will write a instead of x. We can write any dummy variable, minus 1 to the power n jn of a. X we reserve for sign argument. Now if you recall, this Bessel function, they form the coefficient of this series also, so that a to the power j a sine of x is equal to k equal to minus infinity to infinity jk of a e to the power jkx. To verify this series, I mean everything needs a proof. You can easily do that, by using the series expansion of Bessel function, which I wrote, and the power series expansion of exponential function. Okay, so this can be verified. It can be proved also. So we will not do that, but it is easily verifiable. Now my main objective is to show how we got those even terms of Bessel function and odd terms of Bessel function. Now you see this summation. Now I will break it up into two parts. One is k equals minus infinity to minus 1, okay, jk of a e to the power jkx, plus 0, I will directly put j0 of a e to the power 0, then plus k equals 1 to infinity jk of a e to the power jkx, right? So now look at this. All these I can basically put here. Let L is equal to minus k. When I do that, I will get L is equal to 1 to infinity, okay, and then it will be L is equal to, I will write here infinity to 1, then j minus L of a e to the power j minus lx, plus this is simply j0 of a, and then you have k is equal to 1 to infinity jk of a e to the power jkx, right? Now you know this result, so it is L is equal to infinity to 1, and if I write from 1 to infinity, then I will have to reverse, so I write it minus 1. L is equal to 1 to infinity, and this will become minus 1 to the power L, right, j L of a e to the power minus j lx, right? I think minus 1 will not be here. I can simply turn it up. So this will be this, plus summation k is equal to 1 to infinity jk of a e to the power jkx plus j0 of a. Now if you look at these two, you can index them with the same k. Doesn't matter because that turns from 1 to infinity. So I will analyze these two terms first. So it becomes k is equal to 1 to infinity minus 1 to the power k jka e to the power minus jkx, plus k is equal to 1 to infinity jka e to the power jkx. Okay, now we can take the summation as common, and jka also as common, so this is becomes minus 1. No, I will first write the positive term, e to the power jkx minus plus minus 1 to the power k e to the power minus jkx. Okay, so we can write it this way. Now we will break it into two parts. One is for odd terms, the other is for the even terms. So for odd terms you can directly write like this: k is equal to 1 to infinity. I will write here j, this is for even 2k of a. Okay, then whenever I write 2k here, so it will be minus 1 to the power 2k, which is even number, so this will become 1. So I can write e to the power jkx plus e to the power minus jkx, plus the other part will be for odd part, so j 2k plus 1a. Then you know minus 1 to the power 2k plus 1 will be minus 1. So this will be e to the power jkx minus e to the power minus jkx. And you know this will be 2 times cos, so 2 times j2ka cos of kx plus, and this one will be 2j sine of kx. Okay, so it will be plus 2j summation k is equal to 1 to infinity j of 2k plus 1 of a sine of kx. So hence our overall series will become, to call what we are trying to prove is e to the power j a sine x. This was our original series. This is now equal to this whole thing, that is j naught of a plus 2 times summation k is equal to 1 to infinity j 2k of a cos of kx and the next term sine. Okay, now this also can be written as cos of a sin x plus j times sine of a sin x. Now comparing real and imaginary part, this cos is the real part here, this whole is the real part, sine is the real part here, this is the real part. So it means that we get cos of a sin x is equal to j naught of a plus twice k is equal to 1 to infinity j2k of a cos of kx, and sine of a sin x is equal to twice summation k is equal to 1 to infinity j of 2k plus 1 of a sine of kx. So this is the relationship exactly which we have used directly yesterday. I will go back to the book and show it to you. So here you can see the cos of this, it includes only j2 j4, and sine of nx, it includes only 2 times j1 j3. You know, these were used to show that we can write an and bn in this way. So this was just a supplementary lecture to understand the Bessel function concept behind the proof. Thank you.